Hello. In this part of the lecture, we are going to learn about the fundamental building block. And it is a very useful building block that you can find their presence in many analog circuits and applications. So this block is called operational amplifier or op-amp. So the behavior of this block can be simply modeled using a dependent source, as you will see. So when this block is combined with resistors, capacitors, and inductors, those passive RLC circuits, it will allow you to perform various useful functions. For example, signal amplification. So let's look at what this means. So suppose I have a block, and I'm going to say this is my amplifier, and I have an input, and I have output. So input is where you inject or you apply your signal to this amplifier, and output is where you pick up the signal. So suppose I inject or apply a small sinusoid like this. After this input signal, after this sinusoid goes through this amplifier, I expect to see the gained up version of what I put in. Okay, so it's a scaled up version of this little sinusoid. So at the output, I expect to see something like this. Okay, so it's a gained up version, is a scaled up version of what I put in. So that's the amplification of an input signal. What I can also do here is I can have this op-amp perform inversion. So the inversion allows you to present a negative sign to what you put in. And you will see that sign inversion at the output. So for example, if I put in, again, a small sinusoid, but this time I have the input inverted. So after going through this amplifier, I expect to see the same sinusoid. So I'll redraw it over here. It's a gained up version of what I put in, but now the signal is inverted. Similarly, if I put a positive sinusoid, after the sign inversion, I expect to get the gained up version or a scaled up version of what I put in, but I now have phase difference of 180 degrees. Okay. So this is the inversion that I can also perform using this op-amp. Now, what I can also do here is if I have multiple input signals, I have multiple inputs, then I can sum all of them up. So this would give you addition or summation. Apart from a summation, I can also do subtraction. So if I have two signals, I can have one signal minus the other signal, and I can have it, I can have the difference at the outputs. Okay. But of course, after you go through this amplifier, the difference of the signal will also be amplified, will also be scaled. Now, mathematically, what I can also do here is integration. Okay, so it's an integral, right? Just like your mathematical operation. So you do an integral of your input signal, and I can also do the differentiation, right, by taking the derivative of your input signal. So when you combine, so when you hooked up your op-amp with the right passive components, such as resistor and capacitor, you can also perform analog filtering. Right? So you can have low pass filter, high pass filter, and band pass filter, and so forth. And we can also have our op-amp perform some nonlinear functions. For example, I can have it do exponential function, log, square root. Lastly, I can have my op-amp perform analog to digital converter or conversion, and digital to analog conversion. Okay. So this is ADC and the DAC. Okay, ADC stands for analog to digital converter, and DAC or DAC stands for digital to analog converter. Okay, so this is a block that is particularly interesting and useful. It serves as a middleman between the analog and the digital world. So this circuit is very popular, and you can find the presence of this circuit in your computer, cell phones. Okay, so now let's look at how this op-amp looks like, right? And how does it work in reality. So instead of using a box to represent my op-amp, so the symbol that we use for this op-amp looks like this. It's actually triangle in shape. And it has two input signals or input terminals. One is the so-called non-inverting input, and the other one is the inverting input. The non-inverting input is denoted by V plus. The inverting input is denoted by V minus. And I also have an output, which I called VO or V0. And apart from that, I have two power supply pins, and those are for my DC power. So I have positive power supply and the negative power supply. So in other words, an op-amp consists of two input signal or two input terminals and one output terminal. And I have two additional terminals for power. So for example, I can have plus 15 volts and minus 15 volts over here. Okay. So next, let's look at the signal. Okay. So let's just try to focus on the inverting and the non-inverting input. So for the differential signal, okay, I'm going to define something called VI. Okay. So where I stands for my input. And this is equal to VD, where D stands for differential. So VD, so this D here stands for differential. So if I'm taking the input differentially, that means I'm taking one minus the other. So I'm taking, for example, V plus minus the V minus. So I have my non-inverting input here, and this is my inverting input. So I'm taking the difference. So I take the V plus minus the V minus. So this is the so-called differential signal. Okay. There's another type of signal associated with your op-amp. This is the so-called common mode signal. Common mode signal means I apply the same signal at both of these terminals. So the so-called common mode signal, VCM, is equal to V plus V minus divided by 2. Okay. In other words, I'm simply taking the average. So remember, for a differential signal, I'm taking the difference, taking the delta, V plus minus V minus. While for common mode signal, I'm taking just the average. Okay. V plus V minus divided by 2. So far, so good. So we just look at the symbol for this op-amp, and we learned about the signal terminals. And there are 3 signal terminals. Again, we have 2 input and 1 output. And in addition to that, we have also 2 terminals for DC power supplies. Next, let's look at some properties for an ideal op-amp. So I'll be just focusing on the signal terminals. So V plus, V minus, and V out. Okay. Assuming we know how to power the device up by applying plus and minus 15 volts, for example. Okay. So altogether, there are 4 properties for an ideal op-amp. So I'm going to go through all of them one by one. So the first one, okay, the first ideal property is the large open loop gain. Okay, so I'm gonna define this AOL in just a second. So first of all, I have my VI. Okay, so just to reiterate, VI is my input voltage, and this is defined as the difference between V plus and V minus. V plus and V minus. I take the delta here. So this is my VI, and this is also called VD, where D stands for differential. So under the differential mode operation, I want my op-amp to be responsive, okay, to this differential mode, or to this difference in the input signal. Okay. So V out, this is my output. Okay, so V out is therefore equal to AOL times this input signal. Okay, so this is my VI, and this is my input signal. So V out is equal to AOL times VI, where AOL is the so-called open loop gain. Okay, so open loop gain. Right? So A, okay, is usually what we use to denote gain. Okay, and OL, the subscript OL, is used for open loop. Okay. And of course, later on, you're going to see that we're going to introduce this concept with a loop, right? And there is also something called loop gain and closed loop gain. Okay, but first thing first, we'll just for now focus on the open loop gain. Just look at the fundamental definition of it and try to understand the property of this ideal op-amp in this context under differential mode operation. So AOL times VI, okay, and is equal to AOL times V plus minus V minus, right? This is just a rewrite, right? And this is also equal to AD, right? Sometimes different books, they like to use different notation. So AD is another common one that is used to denote the differential mode gain. Okay? So differential mode gain, AD or ADM. Okay, so I use AD over here. So AD times V plus minus V minus. So now if you look at this equation again, this is trying to tell you that if I take the difference between the V plus and the V minus, okay, if I take the delta between these two, and then I send it into this triangle, this op-amp, and then at the output, I'm going to see something like AOL times this difference. Okay, where AOL for an ideal op-amp, okay, for an ideal op-amp is equal to infinity. Okay, so in other words, I'm going to take this small signal, okay, small difference, okay, multiplied by a very large number. Okay, this large number, okay, ideally, I want it to be all the way to infinity. Okay, so I want this AOL, the open loop gain, to be very, very large as possible, all the way to infinity. Okay. Well, so why do I want this? Okay, so if you look at the next equation here, okay, so now I'm going to solve for V plus minus V minus in terms of V out and AOL. Right? So I can move this AOL to the other side. So I have V out divided by AOL. And if AOL is equal to infinity, then V plus minus V minus is equal to 0 mathematically. Right. So this is my AOL. And I'm just looking at this difference, this delta here. Okay. And I want this delta, right? So under this condition, when AOL is equal to infinity, then this delta here becomes 0. Okay. So if this is true, then when you solve for V plus or V minus, right, you will see that V plus and V minus are actually equal to each other. In other words, V plus and V minus, the voltage over here and voltage over here, they are forced to be the same. They are forced to be equal to each other. Okay, simply because I have this large AOL. Right? So if I have some V out, I take this V out divided by this very large number, then V plus minus V minus will converge to 0, forcing V plus and V minus to be the same, forcing the voltage over here and the voltage over there to be the same. And this is one very useful property that we will explore or use later in our examples. Okay, so something like this, okay, so V plus equal to V minus is the so-called virtual short. Okay, so this is one very important statement and observation for you to make when you do your analysis in the involving op-amp, okay, in the examples that you will see in a second. So virtual shorts tells you that even though there is no physical wiring connecting between these two nodes, but virtually, okay, fictitiously, V plus and V minus, they're sitting at the same voltage, sitting at the same potential. Seems that there is some kind of short, right? So virtual wire, right, connecting between these two dots, forcing these two voltages to be the same. Right? So that's the reason why this is called virtual short. Right? It's not just short, but it's virtual short. Right? It's a short virtually. Now, in order for you to claim that you have a virtual short, okay, this one very important property, virtual short, okay, is that not only you need to have large AOL, right, all the way to infinity, but you will also need another supporting condition, the so-called negative feedback. This is a negative feedback. Okay? So in order for you to have virtual short, you need to have, number one, large AOL, how large? All the way to infinity, infinitely large open loop gain. Second, you need to also have negative feedback condition. And this is something that we will also discuss shortly. Okay. So again, the first property when ideal op-amp is to have large open loop gain. Okay, how large? All the way to infinity, as large as possible. Okay, infinity. Let's look at the second ideal property. So the second property is associated with the common mode operation. Okay. So in the first property, we talked about differential mode operation. In the second property, we talked about common mode operation. So in common mode, just like before, VCM, voltage for this common mode, is equal to the average of V plus and V minus. Okay. So I take the average V plus and V minus, and then I can find this common mode voltage. Okay. But what's important here is that I want the ACM, the common mode gain, okay, the common mode gain to be as small as possible. How small? Well, all the way to 0, ideally, right? So now you see the difference. In the differential mode, I want this to be as large as possible, and for the common mode, I want this to be as small as possible. Okay, I'm using A again to denote the gain, and CM to denote common mode. Okay. All right. So let me just quickly illustrate this concept again. So when we say gain, right? So this basically tells you if I put in something small at the input and I get something larger at the output, and I take the ratio, so this is, let's say, V in, and this is my V out. And if I take, just writing over here, V out over V in, okay. So this is my gain, by definition, right? So my gain in terms of voltage, right? So this is my voltage gain is equal to V out over V in. So I take the ratio of this signal divided by the V in. Okay, so the ratio between the two, V out over V in. So that's my gain. And in this case, you expect to see signal amplification, right? So that's because I put in something small, and after going through this op amp, I see something larger at the output, right? So I have signal amplification here. So therefore, my gain in linear scale is greater than one, is larger than one, right? If I have something smaller than what I put in, then this will be called loss, right? So I'll write it over here. If I have a loss, then this means V out over V in is less than one. Okay, so V out over V in is greater than one. That means I have some gain, right? So the signal is amplified at the output. Okay, but if I have something that is smaller than what I put in at the output, then this is the so-called loss. Okay, so it's the opposite case. Okay, so in case one and case two, we're referring this ACM and AOL both as gain. Okay. Okay, so let's look at how do we actually calculate V out, right? So we talked about two operations, right? Two modes of operations. One is the differential mode, and the other one is the common mode. Okay, so this V out, okay, is actually seeing both modes of operation. Okay, it actually sees the contribution from both modes. Okay, namely V out is equal to AD times VD, right? So remember AD is like my AOL, right? And VD is like my VI or V in, right? And ACM is my common mode gain, which is over here, okay, times VCM, which is my common mode voltage. Okay. So your V out actually sees these two parts of contribution. Okay, you have two contributors, right, from the differential mode and also from the common mode. Okay. So in an ideal op-amp setting, right, I want this common mode to go to zero, right? I don't want my output, okay, to see any contribution from this common mode. Okay, so when ACM is equal to zero, then this term here is gone. Okay, so for an ideal op amp, I want my op amp. Okay, in ideal op amp, I want my op amp to react only to the differential mode, to the differential input signal. So again, based on this equation here, I have AD times VD, okay, which is AOL times V plus minus V minus. The term on the right here, this term here is gone because if we assume we have an ideal op amp, then ACM is equal to zero. So this term here is zero out, okay? It's disappeared. So therefore, V out is just equal to AOL times V plus minus V minus. Okay. Now, of course, in this course, we're just treating this block as an ideal op amp, but in reality, this block has to be designed correctly using transistors. And since we don't have perfect transistors, so that means this ACM is not going to be always equal to zero. It may be, depending on the design, it can be some small number, right? But it's not going to be always equal to zero. So if this is not equal to zero, then you will see some contribution due to the common mode operation. And this is one of the non-idealities associated with your op amp in a practical sense. Okay. Okay, so that's why it is important for you to understand that there are two modes of operation for this op amp. Okay, and if we're treating this op amp as an ideal block, then for the most part, we'll look at just the differential mode here, and we assume that in the common mode case, ACM is equal to 0, and we can just zero out this part here. Okay. All right, so now let's take a deeper look into what's inside this triangle, right? And what I can do to model the behavior of this triangle, right? So if I go back to the this page where I mentioned on the second bullet point, I mentioned that the behavior of this op-amp, it can be modeled using a dependent source. Okay, so somehow, we're trying to come up with a simple model to describe how this block functions, okay, and how this block behaves. Okay, so looking into this triangle, I have, so first of all, just focus on this one first. So I still have two input terminals and one output terminal. But when you look inside, right? When you look inside, you will see three more components. The first one is Ri. This is the so-called input resistance of your op-amp. The second one is Ro. This is the output resistance of your op-amp. And then the last one is the dependent voltage source. This is my voltage control voltage source. Right? And how do I tell it's a voltage control voltage source? Well, first of all, it's diamond shape. It's not circular, it's diamond shape, indicating that this is some kind of dependent source. Okay. And this is voltage control because this is based on V plus minus V minus. Okay. The delta in your input voltages. Okay. V plus minus V minus will be over here. Take that number, multiply by some gain, and that will give you this voltage. Okay, so we know that this is a voltage control voltage source. Okay, okay, so if we want this op-amp to behave ideally, okay, so what we really need here is we want this V out, okay, to C, right? So we want this V out to be equal to AOL times V plus minus V minus. Okay, in other words, I want this V out, okay, to see exactly what this voltage source provide. Okay, so I want this V out to be exactly equal to AOL times V plus minus V minus, and where V plus minus V minus is over here, right? The input. And at the same time, right, from the first property, we want this AOL to be as large as possible, right? So that part has to hold. Okay, so AOL has to be still equal to infinity. Okay. So I want V out to be equal to AOL times V plus minus V minus, just like this. Okay, so in order for this to happen, what I need here is I need to make sure this Ri. Okay, so remember this V plus minus V minus, okay, is equal to VD, okay? And this is the same as V in or VI, okay? Input voltage, differential mode voltage, and so forth, or V plus minus V minus, right? They are the same thing in our discussion. Okay? So in order for me to see this VD, okay, and for this to be equal to V plus minus V minus, I really need this Ri to be as large as possible, right? So if Ri is as large as possible, then that means all of the voltage will be dropped across this Ri. Okay, all the voltage will be dropped across Ri. Okay. So when Ri is equal to infinity, is an open, right? So I can say something about the current flowing into this op-amp, right? So if Ri is equal to an open, then the current I plus and the current I minus going into this Ri will be equal to 0, right? Because we know that no current can go into an open circuit, right? So I plus is equal to 0, and I minus is also equal to 0, right? And that's because Ri is equal to infinity in an ideal sense, right? If Ri is equal to infinity, then all this voltage, okay, the difference between V plus and V minus will show up across this input voltage, resistor, okay, which is now an open, okay? And then I can take this voltage, multiply by AOL over here for my dependent source, and then we can move our way to the output such that V out is also equal to AOL times V plus minus V minus. Okay. But of course, in order for this to be valid, right? So what should we do about this RO? Right? If you think about it, I now have some kind of voltage source. Okay, even though it's a dependent source, but we just use an independent source for now. And I have this RO. Okay. This is my V out. Okay. And I have this terminal here grounded, right? Just like this. Okay. So this is my V out. Now, imagine if I connect this V out. Okay, so this is my V out with a small resistor to ground. So let's say this is my RL. And if this RL is equal to 1 volt, one ohm. Okay. So if this RL is equal to 1 ohm, what should this V out be? Right. So let's say this is V in. Okay. Or probably a better name, I'm going to use Vx just so that we don't get confused with this V in over here. Okay. So V out in terms of Vx is equal to, right? It's a simple voltage division. So now you can imagine if I want this V out, okay, to see or to be exactly the same as this Vx, okay, for a given RL, which is 1 ohm, I really need this RO to be as small as possible. How small? Well, ideally, I want this RO to be 0. Now, if you look at this equation, right, this is a simple voltage division here. So if I set this RO to be equal to 0, right, then on the top I have RL, and on the bottom I have RL. RL divided by RL, I have 1. So 1 times Vx, I still have Vx, and which is equal to my V out. Okay. So in other words, if I want to see the entire Vx, okay, appear across these two nodes, I really need this RO to be equal to 0. Ideally, I want this guy to be a short, right? So that's another way to look at, right? When RO is equal to 0, then that means I have a short. Okay. Of course, now if I change this RL to 0.1 ohm, okay, then my VL will still be equal to Vx as long as RO is equal to 0. Okay, as long as RO is equal to 0. Okay. So the last ideal property, okay, is I want this RO to be equal to 0, right? It's like a short circuit, so that all the voltage from the dependent voltage source, right? So even though I use Vx over here, but I really want all of this voltage to show up at the output. Okay, so that's the goal. That's our objective here. So this is sort of something that is very intuitive because if we plug in the right, if we assume the right value or order of magnitude for both input resistance and the output resistance, then we can achieve the result that we want. Okay, so V out is equal to AOL times V plus minus V minus. Okay, so just to quickly recap here, we have four very important properties for an ideal op-amp. The first one is we want this AOL, the open loop gain, to be as large as possible. Okay, as large as possible all the way to infinity. The second property is we want this ACM, the common mode gain, to be equal to 0. And the reason we want this is so that this V out only depends on the differential operation, the differential mode. Okay, because for an ideal op-amp, right, it's supposed to only react to the differential signal only. Okay, so by setting ACM to 0, right, with this ideal case, then this term here is gone. So V out is only equal to this, and it's only responsive to the differential mode operation. Okay, and that's exactly what we want. The third ideal property is that we want this Ri to be equal to infinity, right? So that there will be no current going into the op-amp, and also at the same time, all of this voltage will be dropped across these two terminals, right? And because sometimes, right, you can imagine, right, let's say if I have some resistor over here along the way, right, so this creates another voltage division. So by ensuring that this Ri is as large as possible all the way to infinity, then I can ensure all this voltage is sitting over here. It's going into the it's going into these two terminals, and the op-amp can continue performing the signal amplification. Okay. All right, so the last one is RO. Okay, so RO has to be set to, or it is ideal. In the ideal case, RO should be very, very small, all the way to 0, right? So that's, I can make sure all this voltage will show up across the V out. Okay. Okay, so those are the four properties for an ideal op-amp. And now let's do a quick summary here. Just look at the model again. So for differential amplifier, right? So I have this triangle here, 2 inputs and 1 output, V plus and V minus and V out. Okay. So looking into these two terminals at the inputs, I have my input resistance, which I call Ri. Looking back into this tip of triangle, I have this RO. Okay, so this is my output resistance. Okay. And ideally, my V out should be equal to AOL times V plus minus V minus. Okay, so we've seen this quite a few times already, right? So this is in an ideal case where V out is only responsive to the differential mode. That's all. Okay, there's no common mode components in the context whatsoever. Okay, in an ideal case. All right, and then I can also open up this triangle, and then I can replace this triangle with my model that we just created. Okay, so this will be the model that we can use to emulate the behavior of this op-amp by using some simple dependent source and resistor. So Ri, right? So this is the Ri here, and then we also have the RO. And inside here, we have this dependent source, okay, A times V in, and this is equal to A times V plus minus V minus, okay, right? And to be precise, right, so this A, right, where A is equal to AOL, okay? All right, so similarly, instead of using Ri, right, we know that's for an ideal case, Ri should be equal to infinity, so I can simply just remove that Ri, okay, because now it's open. And also at the output RO, right, I can now replace it with a short. Okay, so I can basically just carry off this Ri and RO in an ideal op-amp model. Okay. Okay, so again, the importance of this model is that if you know how to use it correctly, then it really emulate or mimics the behavior of an actual op-amp. Okay, um, and the beauty of this is that you don't have to worry about the actual implementation at a transistor level, right? Because in reality, this op-amp, this block is implemented or designed based on many transistors. Okay? And this is something that you will learn in the follow-up course. Okay? Okay, so let's look at um, the condition that we need in order to claim virtual short for an ideal op-amp. Okay, so remember in an ideal op-amp, we talked about this very important property called virtual short, right? So for you to have virtual shorts, you need to have two conditions satisfied. One is to have large AOL, and then the second condition is you need to have negative feedback. Okay, negative feedback. And now I like to spend a little bit of time talking about this or introducing this feedback system at a high level, and then we will talk about why you need negative feedback and how does a negative feedback system look like. Okay, so I'm just going to use some simple block diagram. Okay, so I call this the first one H of S. Okay, so you can assign different letter. That's fine. So I'll just follow some classical um, notation in control theory, and you can also use A if you want to. Okay, so H. Okay, and then also beta. Okay. So I'm gonna use this H. Okay, to sort of denote my op-amp. Okay, and it will be hopefully more obvious as to why this guy can be replaced by an op-amp later on. Okay. And then also I have this the so-called feedback network. Okay, feedback network. And this feedback network, right? The assumption here is that it only contains linear passive components such as your R, L, and C circuits. Okay, that's all. There is no active component such as transistor in here. Okay? Only passive components, R, L, and C. Okay. So I have my input, which I call X of S, okay, which is going into this H of S, and I have an output, which I call Y of S. Okay, and notice that this S here, right, this is basically, right, so if you learn something about Laplace transform, right, so we know that this S, is equal to J omega, where omega is your angular frequency. This is 2 pi F. So this is sort of an analysis in the frequency domain. Okay. Okay, so I have this X of S going into this H of S, all right, and then producing some Y of S. Okay. And then I'm also going to tap, okay, part of the signal from the output, okay, at this node and send it back to the input via this feedback network, right? So I tap some signal from the output, connect it to some feedback network, and this signal is going to keep going, and it's going to go back to the input. At the input here, I have, so this is basically my summer with a negative sign, right? So this is going to perform a function as subtractor, right? And sometimes I like to call it a summer with a negative sign. Okay, so it's plus and then plus here, and then with a minus sign here, indicating that you have some kind of subtraction. Okay. So this summer with a negative sign here as a subtractor basically performs a function that I'm gonna take this X of S minus what I have over here. Okay, so X of S minus the signal over here, and that will give me this error signal or whatever this guy is. Okay, so that's how this block works. Okay, so now let's look at mathematically how we can come up with a simple expression to express Y of S over X of S. Okay, so let's start from the let's look at this point here, first of all. So if I were to tap part of the signal from the output and send it back to the input via this beta network, then I know that over here is going to be y of s. Okay, so y of s, the signal is going to go down to the left and then keep going through this beta network. And then at the output of this beta network, I'm going to see y of s times beta. Okay, so that will be the signal sitting right over here. Okay, or right over here. Same thing, right? Because we're looking at the same net, right? It's the same wire, piece of wire. Okay. And just like before, right? So I have a summer with a negative sign. So I'm going to take this x of s minus this signal here, which is y of s times beta. And I'm going to find this epsilon of s that way. I take x of s minus y of s times beta, and then I can find my epsilon of s. Okay. So x of s minus y of s times beta, I will get the so-called error signal. There's an error signal over here. Error signal. And then I'm going to take this error signal, inject it into h of s, okay, whatever this block is, right? But you know that this is going to be our op-amp, okay, later. So I take this error signal, pass it through this h of s, and I'm going to see y of s again, okay? So in other words, y of s is equal to simply epsilon of s times h of s. But what is epsilon of s? Well, from earlier, right, from our last step here, we know that epsilon of s is nothing but x of s minus y of s times beta. So that's this term over here, right? So these two are the same. Right? Simply just replacing this epsilon of s, the error signal, by this term, x of s minus y of s times beta, right? Holding times h of s. Okay. And the next step is just simply solve for y of s over x of s, right? So this is like a output over input, okay? So this is now my transfer function, okay? And there is a name that we use to denote this y of s over x of s, the ratio, okay? This is the so-called closed loop transfer function. Okay, so the reason is called closed loop. So remember a few slides ago, we talked about AOL, right? So over there we say AOL is our open loop gain. And back then there is really no loop, okay? The concept of this loop introduced, right? But now we have a loop, and the loop is going from the output back to the input, right? So this is my loop over here. Okay, so from the output back to my input via this beta network, the feedback network. So now I have to come up with a few different definitions for this transfer function. Okay, so if I were to find y of s over x of s, this is the so-called closed loop transfer function, because I take this divided by this. So now I accounted for this entire operation around the loop, and the loop is closed. The loop is closed. Okay, so therefore this y of s over x of s, the closed loop transfer function, is equal to h of s over 1 plus beta h of s. And this is derived simply from this equation over here, right? Because I have y of s here, x of s here, and I can express this ratio in terms of h and beta. And the outcome of it turns out to be a pretty compact form. Okay, so this is a very classical result out of this feedback system. H of s divided by 1 plus beta times h of s. Okay, so h of s shows up again on the top and also the bottom. Okay, so something important to keep in mind. So h of s, right, this is actually my open loop transfer function, right, or AOL in the context of op-amp, right? So open loop transfer function, because without any loop introduced, if I just look at this h of s by itself in isolation, then this h of s is indeed a transfer function, but in open loop setting, in open loop configuration. Okay, so h of s is my open loop. If I take the product of this open loop gain, okay, or open loop transfer function, and the beta, which is my feedback network, then I have something called loop gain or loop transfer function. So this is simply by just taking the product of these two. Okay. And then I have my error signal. Okay, so this is the error signal shown over here, which is the difference between the input x of s and this signal that is being fed back. Okay, so remember this signal over here is the outcome from y of s, okay, times the beta. Okay, and the difference between this x of s minus this y of s times beta is my error signal. Okay, so this is v plus minus v minus. And then lastly, I have my closed loop transfer function, and this is also called ACL, closed loop gain. Closed loop gain. Because when I take the ratio y of s over x of s, then the loop is closed, right? So if I want to find the gain, right? So this, I can also say this is my ACL, right? And later on, we'll be using this term ACL in the examples, okay, for circuit analysis. Okay, but at a very sort of a general level, right? We'll just say this is equal to closed loop transfer function. Okay. All right. So far so good. So we introduced a few different terminologies here or definitions for the gain. Right. So we have open loop transfer function, open loop gain, right, which we use AOL, right? And we have loop transfer function or loop gain. Okay. And then we also have the error signal over here. And then lastly, we have the closed loop transfer function or ACL, closed loop gain. Okay. Okay, so but we haven't talked about why this feedback or negative feedback is important, right? We briefly talked about this feedback concept, right? So that is by introducing some kind of feedback network, and then we tap part of the signal from the output, send it back to the input, right? That is the feedback, right? So feedback means you sample some of the signal from the output, and then you send it back to the input. Okay, so that's what feedback means. Right? So this is a feedback system. Okay, it's a very classical one. But then how about this negative, right? So negative feedback, right? So let's look at the next part of the discussion here. So, and in fact, I'm now going to replace this h of s, okay, with my op-amp. Okay, so I'm going to replace this block with my op-amp, and then the beta will still stay there, okay, intact. So beta network stays there, and then this h of s is now replaced by my op-amp. Okay. So at the output, at the tip of this triangle, I have my output, which I call y of s, right? It's following the same variable here. And then at the input side, I have my x of s. Okay. And this x of s, notice that it's going into the positive terminal. I sample part of the signal from the output. I send it back to the input via this beta network. But I send this signal back to the input associated with the negative terminal, not the positive, but the negative, such that I can have this error signal by taking the difference between V plus and V minus, right? So remember, we have this V plus minus V minus, right? This is the delta in my input signal from before. And this is really my input signal. Is really my error signal. Okay, so the delta, right? V plus minus V minus is my error signal. Okay, and this particular setup, after I replace the h of s with this op-amp, works exactly the same as this. Right. So before I had to put this subtractor, right, a summer with a negative sign, right, so that I can have this error signal. But now, once I replace this h of s with my op-amp, okay, over here, and knowing that the input of my op-amp actually performs this subtraction, then I can take advantage of that, right? And when I put this op-amp in this configuration, I have exactly what I just showed you, okay, in the feedback, okay, in the feedback, okay. So then the question is, why do we need negative feedback, right? So why is negative feedback good in this case, okay, in the context of op-amp, okay? Well, so for a moment, let's assume, okay, so let me zoom in here. For a moment, if we assume, so remember, this is my output, and this is my input. So for whatever reason, let's say if I have some disturbance, okay, any disturbance, it can be due to process voltage or temperature variation. Okay, so for any disturbance, let's say this node, okay, is being pulled up, okay, right, because of this variability, process voltage and temperature, right? When this guy goes up initially, okay, I wanted to know if there is a mechanism for me to counteract, for me to pull it back to where it was, right? So momentarily, if we assume that due to the disturbance, this output voltage, this Y of S, is creeping up, it's going up. I wanted to know if there is one mechanism or any mechanism that I can use to fix this point, okay, such that I can stabilize this output voltage. Okay. And then the answer is yes, right? I'm going to make use of negative feedback, not just any feedback, but negative feedback, okay? The feedback has to be strictly negative, right? So that I can make this work. And let's see how this works. So if this point here goes up, okay, then this point also goes up, right? Because they are tied together. It's the same point, same net, right? Same wire. Similarly over here, it also goes up. Okay. So far, so good. This beta network, okay, in the extreme case, if I assume that this beta network is replaced, right? So I can put a resistor here or a capacitor, but in an extreme case, let's just say I hardwire, okay, between this node and this node. Okay, so that means this point here is also going to go up. Right, so my starting point is over here. This guy goes up, right? Due to some disturbance, this guy goes up, this guy goes up, this guy goes up. Hardwire for my beta network, this point will also go up. It's the same net, right? So that means this point here is also going to go up. Right? So far so good, right? I'm just using these arrows to indicate the direction of this voltage, whether it's going upward or going downward, right? I'm interested in looking at the trend of it, right? The trend. Okay. So if this point is going up, right, for a given input voltage, right, for a given input voltage, that means it's fixed, right, and it's not changing. If the input voltage here is fixed, then let's look at what happened to my error signal. If the input voltage is fixed, then this point is going to go up, right? This point is going up, right? So my error signal is going to go down, right? This is my X of S, which is this voltage over here, and this is fixed. If the voltage at the negative terminal is going up, then that means the room, right, the actual room between these 2 points is actually going to decrease. Okay, that means my error signal is going to go down, right? So in other words, right, if you look at this expression here, I have V plus here, I have V minus here. If V plus is fixed, okay, and V minus is going up, then the delta between V plus and V minus will be smaller. Therefore, your error signal. Okay, so I'm going to get a smaller error signal in this case. Smaller error signal multiplied by the gain of this op-amp. Okay, if I just focus on the trend, right, I know that this is going to go down. I have smaller error signal multiplied by a fixed gain. Okay, so as a result of that, if I look at the relative scale, right, the trend of it, then this point is also going is going to go down. And if you compare with what we started earlier, right, we assume that we have some disturbance, and that disturbance is causing this node voltage to go up. But now, after going around this loop with the negative feedback, this voltage here, after it goes around the loop, is counteracting what we started originally. Okay, it's sort of compensating for that error, right? It's basically trying to get rid, right, or undo that error, that variation that we started off with. Okay, so by using negative feedback, I can help stabilize this point. Okay, and if you just look at the arrow, this guy goes up, right, at the beginning, and after it goes around the loop, okay, because of this negative feedback mechanism, at the output, at the same node here is actually pulling this node back down, right, such that you can stabilize your output voltage. Okay, and of course, you can also use this the opposite arrow as well, right? So I can probably change to a different color. Try this. So if I start off with something that is going downward, right? Because now my disturbance is going in the opposite direction, okay? And then I have something that is going down, okay? Just look at the color here. And after going through this beta network, okay, this is also going down. The error signal here, right? Or this voltage associated with the negative terminal here is also going downward, okay? So for a given V plus minus V minus, where V minus is going downward, okay? So that means my error signal is going to go up. So when I have an increasing error signal, larger error signal, multiplied by the same gain, AOL, then this point is going to be pulled back up, okay? Counteracting where we just started, okay? So again, the negative feedback works to compensate or to remove this disturbance, okay, by counteracting where what you have originally, okay, in the system. Okay, so it helps to stabilize your output voltage quite conveniently using this negative feedback technique. Okay, okay, so just to quickly summarize here, if you want to have a stable system, okay, the feedback strictly has to be negative, right? So that is the reason why negative feedback is the second condition that you will need in order to justify that you have a virtual short, right? Because remember, to have a virtual short, you want this error signal to be to basically converge, okay, to zero. Okay. Okay, let's look at the expression again. So y of s divided by x of s is equal to h of s over 1 plus beta h of s. Okay. So this can also be written if you want to, right? So I can replace h of s with AOL, right? Knowing that now, AOL is the open loop gain of my op-amp, right? So I can just say AOL divided by 1 plus AOL times beta. Okay, so I'm swapping the AOL and the beta position. Okay, but these two equations are the same. Okay, so now I'm going to make a very important observation and also assumption, which is if my loop gain, right? Remember this term here is my loop gain. Okay. If my loop gain is much, much larger than 1. Okay. If my loop gain is much, much larger than 1, okay. Loop gain basically is the product of this block times this block. Okay. The gain of the op-amp times this beta. Okay. So if this product is very, very large, much, much larger than 1, then I can make this mathematical simplification that y of s divided by x of s is nothing but just 1 over beta, right? So this is gone, right? If AOL times beta is much, much larger than 1, then I can simply ignore this 1 here, and then I can cancel AOL top and bottom. So then I ended up with simply just 1 over beta. Okay. So what is the importance of this this trick, right? Well, remember y of s over x of s is a closed loop transfer function. And this closed loop transfer function is actually my ACL. We go back to this schematic here, or this block diagram here. Y of s over x of s is basically the ratio of this versus the input, right? It's output versus the input, okay? This is basically your ACL, and this is what you're interested to know, okay? So that you can understand the gain, the voltage gain, okay, under this closed loop configuration. Okay, so this is what we're interested in. Okay, but what this is trying to tell you here, right, is that if I have a very large open loop gain, much, much larger than 1, then my ACL depends on only the beta network. In other words, there is no dependency on this op-amp anymore. Okay, right? So ACL now is simply equal to 1 over beta. Okay, you don't see any AOL involved in this final ACL expression. But of course, in order for you to arrive at this step, right, this simplification, over here, we need to know, well, we need to justify that this loop gain is much, much larger than 1, right? AOL times beta has to be much, much larger than 1 so that you can arrive at this 1 over beta, okay? So then the question is, how do we justify that loop gain is much, much larger than 1? Well, if we assume beta is some small number, okay, so, or some kind of passive, consists of some passive component with some ratio, okay. If you look at this AOL here, in the ideal setting, this AOL should be infinity, okay. So infinity times some small number, some fraction, let's say 0.1 or 0.01, doesn't matter because we know AOL is so large. How large? Infinitely large, right? So infinity times beta, this product here, which is my loop gain, is always much, much larger than 1, okay? In an ideal setting, right? So if we say our op-amp is ideal, then we know this AOL is always going to be very, very large, all the way to infinity, such that this condition here, this loop gain much, much larger than 1 condition is always satisfied, okay? And as a result of that, the ACL is simply just 1 over beta. Okay, so that's the beauty of knowing how to make use of these ideal properties, right? We can simplify ACL, right, by just looking at the beta. And in fact, if we know beta, we just take the inverse of the beta, then we can calculate ACL right away. Okay. Okay. So let me just recap here. In order for you to claim you have virtual short, you will need to have 2 conditions satisfied. The first condition is you need to have large AOL. Okay. So this AOL has to be AOL into infinity as large as possible, a large open loop gain. And then the second condition is you need to have negative feedback. right? So the negative feedback allows you to minimize this error signal, okay? So you can keep this error signal small so that V plus and V minus will always be very close to each other, very close. Okay? Ideally, obviously, we want them to be equal to each other, right? But practically speaking, we can only try to make them as close as possible, right? When you, let's say, later on design your op-amp at a transistor level, right? We will try to make V plus very, very close to V minus, okay? But in an ideal setting, yes, this is what we want. And this is the more of a practical. Okay, all right, so I wanted to switch gear to look at some examples, and I'm going to start with the classic examples first. So this is the inverting amplifier configuration, and then we'll look at the non-inverting amplifier configuration. So in an inverting amplifier configuration, I'll just quickly mention the key point here, and then we'll go through this together. So if you look at the closed loop gain, V out over V in. Okay, so that inverting amplifier, the inverting part, actually indicates that you have a negative sign. Okay, you have a negative sign associated with your closed loop gain. Okay, inverting amplifier. Okay, so how do we tell whether this amplifier is inverting or non-inverting? Well, so this has to do with the configuration of your um, of your circuit. Okay, so this is what I'm going to discuss next. So I have this triangle here, right? This is my op-amp, and I have my output, okay, at the tip of this triangle, and also at the output, I loaded it with this RL, okay. And I have this resistor R1, okay, and resistor R2. So in resistor R1, I um, I have this voltage source connected to resistor R1 and then to the V minus node, okay? And then from the V minus node to the output, I have this R2, right? So immediately you can tell that there is some kind of feedback, right? Because I have part of the signal from the output and send it back to the negative terminal of the input, okay? So I have two resistors and I have V in and V out here. And then the question that we need to answer here is what is the gain, right? What is the closed loop gain, okay? And that closed loop gain right over here is V out over V in. And this is what we need to find. Okay, this is what we need to find. Okay, so ACL. Okay, so where do you start, right? So I think that's one very important question for you to to understand, to know, so that you can come up with the right strategy, right? Look at the big picture first, right, before you start working on the equations, okay? So the general strategy is as follows. So first of all, you need to look for virtual short condition, okay, in this kind of problems, okay? So how do you claim you have virtual short? Well, so we have two conditions that we need to satisfy, right? So the first one is we need to have large AOL, okay? So let me just write it down here again. So virtual short. So number one, number two. Number one is you need to have large AOL, right? Going to infinity. And then the second condition is you need to have negative feedback. Okay. So so first of all, do we have large AOL, right? Do we have AOL that goes to infinity? Okay. So this is kind of one intrinsic assumption that we will say yes. Okay. So simply because this is introductory course, so we assume that we'll be working with ideal op-amp. Okay. So in that case, we always say that the AOL is very, very large, right? And we can assume that the AOL is always uh, so large that we don't have to worry about this non-ideal the non-ideality. Okay, so we assume that AOL is yes going to infinity. Okay, but then for the second condition, negative feedback, this is something that we have to check. Okay, so one thing that you check, right, as I mentioned earlier, you look at the signal, okay, going back from the output to the input, okay, and the signal that goes back from the input, okay, going back from the output to the input has to go into the negative terminal, okay. So in other words, this is my output. I have this feedback network, okay. Part of it is my R2, okay. So through this feedback network, the signal has to be eventually going back to the negative terminal of your op amp, not positive, okay. If it's going back to the positive terminal, then you have positive feedback, and the positive feedback is bad in the context of amplifier because it will only make your system or amplifier less stable. Okay, and if you're not careful, it can become an oscillator, right? Creating oscillation. So for signal amplification for amplifier, right, we always want the feedback to be negative, right? So the way to check again is you look at the signal going from the output back to the input, and that signal has to go back to the negative terminal of your input. Okay, so from here back to the negative terminal. Okay, so now we have large AOL, right? So check, and then we also have negative feedback. So now we can claim we have virtual short. Okay, we can claim we have virtual short, right? So that's the very first step that you will need to do as a sanity check every time when you do this kind of problems. All right, so we have virtual short. So then what's next? Well, so let's look at some of these connections here. So first of all, we have V plus terminal. So maybe I should this color again. So we have V plus here, and we have V minus. Okay, so remember this V minus is associated with this dot here, right? And it's the same as this dot. Okay, so same net, same wire. Okay, so V plus is sitting over here. So V plus is equal to 0 because this is grounded. Okay, so this is grounded. Okay, so now by making use of the virtual shorts, now I can say that V minus, which is over here, this V minus is equal to V plus, right? Remember, virtual short tells you that V plus is equal to V minus, right? So that's what we concluded based on this virtual shorts property, right? So V minus is equal to V plus. And what is V plus? V plus is nothing but 0, right? Because this is grounded. Okay, so we saw this connection, right? V plus is equal to 0, and we made this conclusion knowing that we have virtual short, right? So V minus is therefore also equal to 0. Okay, and then the next one is, well, this is coming from the um, um, one of the properties for your ideal op amp, right? This is having a large having a large input resistance, right? So equal to infinity, right? So when the input resistance is equal to infinity, then there will be no current going into the two terminals, I plus and I minus. Okay, so I plus is equal to 0 and is equal to I minus. Okay, so we have all this background background information ready, right? So now we can proceed to solving the V out over V in. Okay, so we're gonna just use a simple KCL here, and we need to pick a node, right, to write our KCL equation or nodal analysis. Okay, so this is based on nodal analysis. Okay, so then the question is, which node should I use? Okay, so remember the objective here is to come up with an equation that relates V out and V in. Okay, so then it makes sense that we look for a point, a node that is shared between these two variables, V out and V in. Okay, directly or indirectly, right? So if I look at this node here, right? So at this node, right, it seems that the V out is over here, V in is over here, right? So if I come up with the equation correctly, then I can sort of relate V in and V out together, right? So this is one natural place for us to write our equations um, using KCL, okay, using nodal analysis. All right, so I have V minus here. Okay, so I'm just going to perform a simple KCL. So V minus V in divided by R1. So this is the current flowing out of the node. So that's captured by this term here. V minus V out divided by R2. So that's the second term over here. All right. So now the next step is also very important, right? Before you set everything to 0, I want you guys to take a look at this third branch, right? Remember, we have 3 branches. So if we have 3 branches, we're supposed to have 3 equations, right? But we just talk about 2 only, right? So this one and this one. The third equation is actually the current going into the negative terminal. And guess what? That current is simply equal to 0, right? And this is simply because Ri is I think I use R in or Ri. Yeah, Ri is equal to infinity. Okay. So this is from the one of the ideal properties that we talked about earlier. Okay. So 3 branches. Okay. So even though in the equation I only use 2, right? So I assume that this is already null, right? So I skipped that one. So instead of saying plus 0 again, right? So I just have 2 terms here, and then I equate this 2 to 0, right? The algebraic sum of all the currents is equal to 0. Okay. So then, and we know that from earlier, right, from the virtual short condition, V minus is equal to 0, right? So I can just get rid of this, right? I can say V minus is 0, V minus is 0, right? So negative V in is equal to um, negative V in minus R1, and this is equal to yeah, so you move this one to the other side, right? So plus 0 minus V out, right? So you move this one to the other side, so you have positive V out. So then the rest is you just solve for this V out over V in. So this is your ACL, okay? And it's a simple ratio minus R2 over R1. Okay, and with a negative sign, right? So when you move this to the other side, you have plus over here, and you have minus on the other side. So when you take the ratio, you still end up with a negative sign. Okay, so earlier I say that, right? We have an inverting amplifier configuration, and this will give rise to this negative sign. Okay, so the inversion gives rise to the inverting amplifier. Okay, so that's important to keep note of. Okay. So if you look at this equation, so my ACL, my closed loop gain is equal to the ratio, okay, or is set, right? This gain is set by the ratio between R2 and R1, right? So by choosing the right value for R2 and R1, you can set the gain, right? You can decide how much you want to scale up your input signal, okay? So in other words, V out is equal to minus R2 over R1 times V in. So if I put in, right, so if I put in, let's say, positive sinusoid at the input, and then at the output, I expect to get a negative sinusoid, but a scaled up version of my negative of the input signal, right? And it's going to be scaled up based on the ratio R2 over R1. Okay, and the negative sign immediately tells you that you're going to get a negative sinusoid because you have this sign inversion. Okay, sign inversion, right? Okay, so I should probably be a little careful here. So I'm using this oops. I'm using this entire block, okay, to denote this circuit. Okay. So inside this triangle here, right? I call this, right? This is a symbol for my amplifier, right? And I'm using this to denote everything, including this op-amp with a resistor R1, R2, and so forth, right? Such that when I inject this input signal, and then I have the output signal over here. Okay? So there's a subtlety there. Just wanted to make this clear. Okay, let's look at the next configuration. So the next configuration is the non-inverting amplifier. So in a non-inverting amplifier, if we look at the ACL, right? So this is my ACL. So as you can expect, I don't have any negative sign, right? There's no sign inversion. Okay? So it's a non-inverting amplifier, a positive gain. So let's look at how we can arrive at this ACL. Right. So first of all, you know, as a sanity check, we always need to ask ourselves, is there virtual short in this op-amp, right? In this amplifier. Okay. So then the answer is yes, right? Because first of all, we know that we're dealing with this ideal block, right? So we assume that AOL is always very, very large, all the way to infinity. And then second, we need to check for negative feedback. So this is my output, right? I sample part of this output, send it back to the input, okay? But this input, okay, this signal is going back to the negative terminal of your op-amp, okay? Which indicate that you have negative feedback. Okay. All right, so let's look at the non-inverting configuration now. So if you compare, if you look closer, if you take this guy, all right, if you compare this with this, okay, what seems to be the difference that makes one inverting and the other one non-inverting? Well, there's feedback, right, going from the output back to the input, and it's also going back to the negative terminal, right? That's all fine, right? But what is setting one different from the other, right? So that one is negative, one is inverting, and the other one is non-inverting. Well, take a closer look at where this input signal is applied or injected. In an inverting configuration, inverting amplifier, right, this input signal is going into the negative terminal. Right? For the non-inverting amplifier, this signal is going into the positive terminal. Okay, so that's basically the reason why one is inverting and the other one is non-inverting, right? It depends on where you inject your signal. Okay, and of course, you know, the place where you picked up your output is always the same. Okay, so by changing the location of where you inject or apply your input signal, the input voltage is going to change this. It's going to give rise to the negative sign. Okay, so for non-inverting amplifier, you always apply your signal to the positive terminal. Okay, so now we know that there is virtual short. So we can already write down this statement: V plus and V minus are equal to each other. Okay. And what is V plus? Well, if I apply my signal at this node, right, or to this node, then I know that V plus is nothing but V in. Okay. So in other words, V minus is also equal to V in. Right. So and this is due to the virtual short. Right. So if you know how to make use of this property, right, then you can simplify a lot of steps in the process, right? Because you know that V plus and V minus, they're actually the same. And if V plus is equal to V in, then V minus has to be equal to V in as well, right? And that will simplify your nodal analysis a lot. Okay, and then the second statement here, right, just like before, right? I know that the input resistance is equal to infinity, so I plus and I minus are both equal to 0. Okay, so now let's write our nodal equation. Okay, so where do you pick your node to write your nodal equation? Well, if I start from here, right, this node here seems to be a reasonable place because it kind of relates V out, okay, and V in a way, right? So I can write my equation there, and then I can solve for V out over V in. Then we're done. So I'm going to use V minus, right? So V minus divided by R1. So that's the current flowing through this R1 to ground. Remember, this node is V in, and this node is also V minus. Same thing as over here, right? It's hardwired. Okay. V minus minus V out divided by R2. Okay, so I have current going down this way, and then I have current going to the right. Okay, so two terms. And of course, where's the third term, right? We have three branches, right? 1, 2, and 3, right? So the third branch is basically captured by this, right? And in fact, it's I minus, right? So the current going into the negative terminal is equal to 0, right? So I'm skipping that one here. Okay. So two terms here, right? So branch current 1, branch current 2, set it equal to 0. And we know that V minus is equal to V in, right? So we might as well already, right? This is V in. This is V in. Okay. So this is V in, and this is V in. Okay. So we have one equation and we have V out and V in. So to solve for V out and V in, that becomes very straightforward, right? We just need to move things around a little bit, right? And then we can we can arrive at this final expression for ACL. Okay? So cross multiply, all right? And then you solve for V out, and you move V out, or you solve for V out over V in, and you're gonna see the ratio R1 plus R2 over R1. Okay? And you can further simplify this into 1 plus R2 over R1 with a positive sign. Okay? So the positive sign again indicates we have non-inverting amplifier. Okay. And perhaps I'll just quickly relate the outcome of the ACL to what we just discussed over here, right? So remember, in the earlier discussion, we have ACL equal to 1 over beta, right? So it seems to tell us that the ACL is independent of your op-amp, right? If we are treating this op-amp as an ideal block, okay? So ACL is equal to 1 over beta, okay? So for an inverting amplifier, we know ACL, right, from before is minus R2 over R1. Okay, so probably rewrite it over here. Right, so ACL is equal to minus R2 over R1. And this is also equal to 1 over beta, right? So now you can identify this beta quite easily, right? So beta is nothing but the inverse of this minus R2 over R1, right? So this is simply minus R1 over R2. Okay, so that's your beta. Okay. So similarly for non-inverting amplifier, so your beta, right, is simply equal to R1 over R1 plus R2. Right, so you take this guy and then you invert it, and that will be your beta. Okay, so all there's to say is that if you know beta, then you can simply just take the inverse of that beta, and you can find your ACL as well, right? And if you look at this op-amp, non-inverting op-amp configuration, right? So we're basically taking or sampling part of this signal from the V out, right? And then pass it through this beta network, which consists of R2 and R1. This is V out, right? And from there, you can determine your beta network, right? Which is basically just a ratio, R1 over the sum, right? And R1 over the sum, that basically, right? So this is V in, right? So if I were to find V in over V out now, right? So this is feedback going from the output back to the input, then this is nothing but just R1 over the sum. Okay, so then this is your beta. Okay, so beta is equal to V in over V out. okay, in this case. And this is simply just R1 over the sum, right? So going from the output back to the input and going through this voltage divider, voltage division. Okay? And from this beta, take 1 over the beta, you can find your ACL. Okay, so that's one trick that I wanted to show you. Okay. Okay, so next example, we have the so-called trans resistance amplifier. And for trans resistance amplifier, the idea is that instead of finding the ratio of V out over V in, now I'm going to find V out over I in. Okay, so what is V over I, right? So V over I is resistance, right? But then we have trans resistance here that basically indicates, it's like a transfer function where I have my input on the one side and the output on the other side, right? So which gives rise to this trans resistance. Okay, so again, I'm going to skip this virtual short sanity check, right? And I think we have done this several times. And the first thing that you need to ask yourself is, do you have virtual short, right? So you have to check AOL and also the negative feedback. Okay, so we have that, right? Because we know the output is going back to the negative terminal. Okay, so we have negative feedback there. Okay, so with that, then we know that V plus, okay, is connected to ground, so it's equal to 0, right? And due to the virtual short, we know V minus is also equal to V plus, and which is equal to 0 as well. Okay, and just like before, I plus is equal to I minus is equal to 0, right? Then we have these two conditions, two statements, and then the rest is solving for this V over I in. Okay, so if I use this node, right, to write my nodal analysis, so the current I in going into this node is equal to current leaving the node. Okay, so what is the current leaving the node? Well, the current leaving the node is equal to V minus, this point here is V minus, okay, minus V out divided by RF, right, where RF is this resistor between V minus and V out. Okay? So I have this current going in here, and this is equal to the current leaving the node, right? And we know that this current, which is I minus, is equal to 0. Okay, so I'm only focused on this current and this current. Okay? So there's current going in, which is my I in, and this is equal to the current coming out of this node, which is V minus minus V out divided by RF. Okay? So and therefore, since V minus is equal to 0, so V out over I in is simply minus RF. Okay, so this is the trans resistance amplifier. Okay, so if I inject current in here, and then I can look at the voltage, right? And the amplification, okay, is based on this RF, okay, the value of this resistor. Okay, so let's look at the next example here. So I have a summing amplifier, and this summing amplifier, if you take a closer look, this is nothing but your inverting amplifier, right? So if you sort of, imagine if you remove these two branches, V2 and V3, it basically comes down to just V1 here going into the negative terminal, right? And then you still have your regular feedback, negative feedback just as before. And this is nothing but the inverting amplifier, right? But then this is a summing amplifier because now I'm going to introduce two more branches, okay, two more input signals, so that hopefully, this V out can, find a way to sum all these voltages together, or in some way. Okay. All right. So similarly, I can claim that I have virtual short, right, due to those two conditions that we discussed several times. And from the connection, we know that V plus, right, is equal to 0. So is V minus, and V minus is sitting over here. Okay, so this is V minus, and then this is V plus. V plus and V minus are the same because of virtual short. So now I just need to write my equation over here, right? Just based on this B minus node. So B minus V1 divided by R1 plus B minus V2 divided by R2 plus B minus V3 divided by R3, okay, plus B minus V out divided by RF. Okay, so I have 4 terms here, right? And of course, we can also say something about this branch, right? So I can say I plus is equal to 0 is equal to I minus. Okay. All right, so I have all these terms, right, and sum to 0. So then the next is I just need to solve for V out, right? I cannot simply solve for V out over V in because now I have 3 inputs, right? So the best I can do here is I can solve for V out, and then I can find a relationship between V1, 2, and 3, okay? So if you do everything right mathematically, it turns out that this V out, okay, is equal to V1, okay, divided by R1 plus V2 divided by R2 plus V3 divided by R3, right? So you do have this summing action like this, right? And of course, you have some ratio, right? So if you look at this equation here, it's probably easier. I have some ratio, okay, which will tell you, okay, the relationship between V out and V in, or VI, or sorry, V1, okay, and also the relationship between V out and V2, right, based on this, and V out and V3 based on this, okay. But in a way, right, we have V1, right, some fraction of V1 plus some fraction of V2 plus some fraction of V3, okay. So giving rise to this summation action, the summing action. The negative sign that we have over here is not surprising, right? Because the entire topology is based on inverting amplifier. Okay. Okay, so let's look at the difference amplifier. So the difference amplifier is going to take the difference, the delta between V1 and V2, okay, or V2 and V1, and then produce an output, okay, V out. And then if everything is done right, the output voltage will still be a scaled up version of what you put in. Okay. All right. So I have the virtual short, right? Just like before, right? I assume we have large AOL, and then we also have negative feedback, right? So output going back to the negative terminal of your input. Okay. So then I can claim that V minus, this is V minus, and this is V plus, okay, are the same due to virtual short. So I'm going to write 2 node equations, right? So first at this V minus node, okay? And then next at the V plus node. So at the V minus node, I have V minus V1 divided by R1 plus V minus V out divided by RL, or R2. Okay, this is R2. Okay? And this is equal to 0. And this is my first equation. Second equation, I'm going to write it over here. V plus minus V2 divided by R1 plus V plus minus 0, right? I have a ground, right? Divided by R2. Okay. And then of course you have the third branch, right? Which we always assume is equal to 0 because we have large input resistance. Okay. So 2 terms, equation 1 and equation 2. Okay. All right. And based on equation 2, right, I can simplify, I can solve for this V plus, okay? I can solve for this V plus, and this V plus turns out to be a simple voltage division. So V2 times R2 over the sum, right? And which is something that you can also do by inspection, right? If I wanted to find V plus, okay, with this voltage here, V2, right? So I can just use voltage division, R2 over the sum. So I have R2 over the sum here, okay, times V2, and that will be V plus, okay? All right, and then, and this is equal to V minus, right? This is equal to V minus because we have virtual short condition over here. Okay, so from equation 2, we first found this, and then we set it equal to V minus, right? And the reason we wanted to do that is because we wanted to plot plug in this entire term, right? This equation here into here, right? So that we can solve for, or we can find a relationship between B out and B1 and 2. Okay, so substitute 3 into 1. Okay, so substitute this into this. Okay. And I show you all the steps here, and you can go over the math here, and you will see that the outcome of it is V out, okay, which is equal to some ratio R2 over R1, okay, times the difference between the two input voltages, V2 minus V1. Okay, so V2, right, is the voltage associated with the positive terminal, and V1 is the voltage associated with the negative terminal. So I'm simply just taking the difference between V2 and V1, all right, and then multiply by the ratio R2 over R1 so that I will get the output voltage, okay? And if you set your R2 and R1 ratio correctly, you will get a Genda version of that, okay? The Genda version of this, the difference between V2 and V1. Okay, following this equation. Okay, so one more example, numerical example here. So zoom in here. Okay, so over here I have so this is the the topology here shows that I have my input signal here going into a positive terminal. Okay, so well, before you start doing anything, right? Perhaps it's a good idea for you to first look at the circuit for a little bit, and then try to strategize what you wanted to do, right? To find the output voltage, okay, and or V over V in, okay. So in this case, you realize that the input signal is going into the positive terminal, right? So this kind of tells you, right, as a reminder that this is based on inverting or non-inverting amplifier configuration, okay. So the output, okay, if you do everything correctly, should give you a positive number, okay. It should give you a positive number, right, because of the non-inverting amplifier configuration. Okay, and then so now let's look at the numerical calculation here. So first of all, we're gonna again assume that we have virtual short, right? Because we have large AOL and we have the output going back to the input, right? But it's going back to the negative terminal of your op-amp, okay? So we have these two conditions satisfied, so therefore we have virtual short, okay? So that's good. All right, so then what I'm going to do here is I'm going to first write an equation at the input, right? So I'm going to take V in, okay, minus V plus, okay? So minus V plus. So the idea is that because I wanted to understand, okay, the relationship between B in and B plus, okay, so one way I can do it is, I can write this equation. So this equation here is based on knowing that the current I plus going into this positive terminal is equal to 0, okay, and also the fact that the voltage here, V in minus V plus, okay, divided by this 1K ohm, right, which is this current, okay, has to also be 0. Okay, so V in minus V plus, okay, divided by 1K is this current, and this current has to be the same as this current I plus, and which is equal to 0. Okay, so based on this, I can deduce V in and V plus are equal, right? So if this is equal to 0, right, so then I plus is equal to 0 can be satisfied. Okay, so that's how I arrive at this conclusion. Okay, so V minus is equal to V plus. And because of virtual short, this V plus is also equal to V minus. Right, so I'm doing two things at the same time here, right? So V in is equal to V plus is coming from this statement here, this equation. And then V minus is equal to V plus. That's because of the virtual short. Okay, All right, and then let's move on. So I try to show you a slightly different approach. Instead of writing the nodal equation, okay, so what I can do is I can make use of voltage division because personally I feel it's easier. Okay, so I'll show you how I approach that. Okay, so um, knowing that this node, okay, is B minus, okay, and knowing that B minus is also equal to B in, right? So from this statement here. And if I wanted to find BA, right? The reason I wanted to find BA is so that I can later on find B out, right? So, but before then, we need to first find BA, right? So to find BA, right, you can go through your nodal analysis, no problem, right? The one easier way to find BA, right, is by, by inspection, by knowing that I have this VA, right? So suppose my VA, right? This is my VA, and I have this resistor, 10K ohm, and then I have another resistor, 2K ohm, and then I have a ground, right? And then at this point, which is this point over here, right? This is my V in, okay? So I try to simplify this problem so that, I can use the voltage division, okay, to find my VA, right? I can set up a simple equation like this. V in is equal to VA times 2K over the sum, right? 2K because, I wanted to find the voltage drop across this 2K ohm resistor, okay? And this VA here is this point over here, okay? So if you know how to do this by inspection, right? So you can, if you see this, right, you can use voltage division to find VA very easily, right? Because uh, V in is equal to VA times 2K over the sum, right? This is from your voltage division. So now you can just go back and solve for VA, right? Move things around, right? Because we know V in already, right? V in is given to you 0.5 volt, right? So this is 0.5 volt, and you can solve for VA, okay, numerically. Okay, so VA turns out to be 3 volt. Okay, so then the question is, what is IL and what is V out, right? So very straightforward. To find V out, we just need to do another voltage division. Okay, so we will take 3 times 2 over the sum. Okay, so 3 times 2K over 5K, right? Over here. So VA is 3 volt. And this is 3 volt times 2K over the sum. And voltage division, 2K over the sum. All right. And then what is IL, right? So IL is this current passing through this 3K ohm and 2K ohm, right? So what I can do is I can take VA divided by the sum of these resistors, okay, 3K and 5K, okay? So VA divided by 5K, or I can just simply take V out divided by 2K, right? So if I know this V out already, voltage divided by the resistor, Ohm's law, I can find my current IL, okay? And it turns out to be 0.6 milliamp for IL and 1.2 volt for V out.